Alright, dear students, let us look at our historical tower and create our first views in Paraview, where we today want to look at the surface pressure of the historical tower as a first sanity check if the simulation makes sense, and look at the flow field around the historical tower by means of some slides and vector fields. So hit the start button on the bottom left and then type blue, and you should see something like this: blue CFD core terminal. Left click and this blue CFD terminal opens, and you can see open foam is loaded, and we go directly to our main directory of the historical tower. For me it's located in D, so CD for change directory and then D colon. For you on the SIPL it might be Z, right, for your student Z drive. So CD, D, and now you can see in this line here we are located in D. LS for list, and this shows everything that is inside my D drive on the hard drive. And we want to go here to the historical tower, so I'm typing CD space, now hitting the H button, and after hitting the H button I just hit the tab button, and this will auto-complete the folder name historical tower. So change directory CD historical tower. We're now in the main directory of the open foam simulation. We type ls again, and this is for list, and here we see some files and folders. We will discuss them later on. For now we will mainly deal with Paraview and get a first idea about how the simulation look like. So we start Paraview with the means of a script which is called parafoam, which loads the software Paraview, and this is a script which helps Paraview to load this open foam case so that we can post processes in a 3D graphical user interface that is Paraview. So hit enter after the command, and rather quickly Paraview should open. There is some information first. We don't need this all the time, so just hit don't show this windows again, close, maximize. You can see the historical tower with the extension .foam is loaded here. This seems fine. Before we hit apply, we first want to have a look at the geometry only. And you might not know this as of right now, but I'm telling you now. The geometry consists of multiple parts, and they are called the bottom part, the pyramid, the Stolperkante, which is a small edge where the flow separates, and the tip. Select those, deselect internal mesh, hit apply. This now takes a little moment, and here we can already see the geometry. So if you select and deselect those parts, you can check which is which. Obviously the bottom part is the part here down below. Now we can see it here in the legend, where you can drag it around with left click, that we are dealing with P, and P is the pressure. Here on the top you have a drop down menu, can show all of the other variables if you like. And first question that we might have is, what is the main flow direction here? If you like, stop the video real briefly, and just by looking at this tower here, what could be the main flow direction? So the main flow direction is the positive x direction, as we see here by this red arrow at the bottom. How do we know this? Well, we have very high pressure here, right, where the dynamic pressure of the inflow hits this side of the building. We call this the roof side sometimes, and the dynamic pressure can then become static pressure on this building. We see red is high here in this legend, right? As for right now, we don't care really about the values. We just want to get qualitative insight into this tower. So by the way, rotating is just holding left click here, then you can rotate. Zooming in and zooming out is the mouse wheel, and just taking it up and down is holding the mouse mouse wheel, and then you can drag it around the whole thing. So what else do we see? Well, we see that here is a blue area, and here also is a blue area. This indicates that on this sharp edge here the flow separates, and then after flow separation you often find areas of high suction, so to speak, so negative pressures, negative of course with respect to the atmospheric pressure or a reference pressure that is defined in the CFD simulation. We'll talk about this a little bit more. So what we also can do, we can shift the range that is shown here by going here on the top, rescale to custom data range, and let's decrease the range a little bit from -300 to 120. Rescale, so we can see it a little bit better. Now on the sides here you see there is somewhat suction too, and then what you often found around this bluff body is on the back side, we sometimes call this lay side, you find a rather constant suction everywhere, and as we will see, it has quite significant flow separation here and vortices on the back where the flow tries to fill the empty space after flow separation, creating vortices. And when we drag the legend here, where we maybe here somewhere in this region of negative pressures, it's kind of hard to tell. Of course we will be able to get it more accurate later on, but as of for now it seems definitely reasonable what happened here. If we want to see the mesh, we go here to top, surface, and then surface with edges. Now we get an idea about the surface mesh around this historical tower here. Okay, after we've now seen the mesh and the pressure, let's go to this information tab here. It gives you some information about the geometry or whatever is chosen right now in the 3D viewer, and there is some general information, the number of cells on the surface of this thing right now, and you also see the bounds. This is the X, Y and Z range, and you can see this tower is only around 22.8 centimeters high, so the units here in meter, indicating that this is not the full-scale tower in reality, but rather the size that was also used in a wind tunnel experiment, and we will talk about the experiment in the upcoming session. Okay, so let us go back, select the historical tower here, go to properties, deselect the geometry parts and select internal mesh only, hit apply. This takes a moment again depending on your machine. Now the whole case is loaded, and when we zoom out, now I'm using the mouse wheel here, we see this box. And now ask yourself, how do we call this box? Well, we call this the domain or the numerical domain, right? We have discussed this already about potential size of such a domain, and you see the tower here. Now again, the flow is in positive x direction, so this is here the inlet, this is the outlet, right? This is the ground, and so on. And what we will do now is analyze the flow field even more, or we start analyzing the flow field a little bit. We only did pressures as of right now, so we tried with the slice first. Here at the top you have a filter called slice, and some of the filters that you can use in OpenFOAM are shown here at the top. However, one of the most convenient ways of adding filters is a shortcut. I'm hitting on the keyboard now Control, or Steuerung in German, Control and space, and this pops up, and now I'm just typing slice, and all filters that are applicable which have this string slice here inside are shown. We take slice, I first left clicked on historical tower here on the left in the pipeline browser, hit OK, or hit the slice button there, and now I want a Y normal slice So I click on Y, right? The normal vector of the slice points in the Y direction. So we cut in the longitudinal direction, if you like. Deselect show plane, otherwise we can still move it around. And then hit apply. Now we only have a small slice of the domain, right? That makes sense. Okay, so what we now want to do is we want to increase the time here. So we go to the last frame on the top. This is basically the result of the simulation, the final result. And then we want to see the velocity field. So in the drop-down menu here at the top, we select U. Now this gives us some more information about the velocity field. You can see at the inlet here on the left, low velocity at the bottom, high velocity at the top. So this already indicates that this might be an atmospheric boundary layer, right? We will look into this in more detail later on during the course. As of right now, you might want to believe me. And you see, of course, somewhat small values of velocity here in front. This indicates some or some eddies that appear here, and then very small velocities also here on the back. And this one we want to investigate a little bit further. So how is the flow direction here? Can we maybe see some vortices around the flow? And this is something that you see very often with bluff bodies, where the flow separates from the body in the wake. So on the back side, we call this the wake, you see rather low velocities after flow separation. But we will also find some regions of accelerated flow. For instance, here at the top we see some regions of accelerated flow. If we like, again, we can change the range of the velocity. In this case, it's the magnitude of the velocity vector. You can see it here in the legend, right? U magnitude. This is why it's never negative. So let's try something like from 2 to 20 maybe. Let's see if this enhances the view. Yeah, maybe a little bit. We see the flow acceleration here, and then large regions with rather low velocities. That is the magnitude of the velocity vector. Okay, let's investigate this a bit further. We click on the slice, left click on the slice. Again, we are looking for a filter here, and the filter shall be, so control space. The filter that we need is surface vectors. So surface vectors, select this one, then click on this button here. Surface vectors is now applied to the slice. Just hit apply. What this surface vector does is, clearly a velocity vector is usually three-dimensional, right? Component in all of the three directions of the Cartesian coordinate system. And surface vectors makes it a 2D vector, let's say. So we can show the arrows or the vectors in 2D on this slice that we created, which helps us get a better idea about the flow. So when I selected surface vectors here, for some reason I jumped to pressure again. We remain with the velocity u here for now. And now the final filter that we use is glyphs. So again, control space GLY, and here we have the glyphs vector. This one now can use the surface vectors that were just created by the filter and show the direction of the flow field. So select the glyphs vector, you can see it here. Now I already know that when we hit apply here, we won't see that much. Scale array. This is, should the arrows that are created here by the glyph type be scaled by some scalar in the flow field, or even by some vector. For now, we just want arrows that have the same size. This is really comfortable for visualizing the flow field. So no scale arrow. And I already know that this scale factor here, it's just the size of each individual arrow, is probably too large. So instead of using this default value here, I'm using 0.01, and we probably refine this anyways. let's hit apply for now, and we see some arrows already here, but it's not a perfect visualization or great visualization. The coloring is still by the pressure, right? You can see it here. The color changes a little bit in the different regions. It's hard to tell, but those are more orange and those are a little bit more red. We have seen the pressure already a little bit, at least on the surface of the building. So the coloring should just be a solid color, and white might be fine, but I go to edit and take black. I think this visualization is a bit better. This looks already quite nice. I believe what we need is just more arrows to get a better idea of what's going on. So maximum number of sample points, increase to, this is now 500,000, 500,000. Hit apply, and now we see much more information of the flow, about the flow field. I'm zooming out and zooming in with the mouse wheel, and you see that there are much more arrows here around the building than in the domain, and this is due to the finer mesh here. So Paraview will show more arrows where we have more cells located. How do we know that we have more cells here? Well, we can just go again in the top, surface with edges, but selecting the slice here first and then surface with edges. Unfortunately, this doesn't work as intended. Deselect surface vectors and glyphs by deselecting them with the eye here, right? If the eye is closed, this symbol, the eye is closed, you will not show it in the 3D viewer. And here at least we get a general idea about the mesh. There are some weird lines, and also the cells are triangulated. Here's an option. I'm in the slice 1, triangulate the slice, deselect, hit apply, and now this looks better. This is kind of the mesh that was actually created, with the exception of those weird lines that you see here. This is just some bug or something where OpenFOAM is not perfectly compatible with Paraview. If someone knows how to remove those lines here, I appreciate it. Anyways, we go back to the glyphs. So we show everything again. We show the glyphs. Very nice. And now we see how the flow performs here around our historical tower, right? Of course, it's deflected here. We see this vortex here where the flow impinges on the structure. It says nowhere to go except up and down, and thus we have this vortex here. Then it is with the pyramid, it goes somewhat parallel to the pyramid, and then of course it needs to go around here, and then it separates here, and on the back, of course, as it separates from the flow, from the structure, this needs to be filled, right? This region here needs to be filled, so the flow comes back here, and we have this very huge vortex in the back that we will often see around bluff bodies here. Now this is actually only a 2D view. In fact, the flow is quite more complicated. And how do we see this? Well, let us go back to the slice. It still has the filters, and now instead of having this Y normal slice, let us try a Z normal slice and hit apply. Now this Z normal slice is rather high. You can see it here. The origin is at 0.68, somewhere at the top of the domain. We want to go a little bit more down, so let's say 10 centimeters. I believe the tower had a height of around 23 centimeters or so. So let's go down, and now we see that we are cutting around the bottom part of the domain. Now let's zoom in a little bit, and here we have even better view, or another view of the flow. And here we see the flow separates on the, let's say that's the left edge of the bottom part, and that's the right edge of the bottom part. but the flow separates here as it cannot follow the sharp edge of the geometry. Separates here, and then we can also see that there is some recirculation area here, right, where the flow arrow actually points against the main flow direction or opposite to the main flow direction, indicating that we have a vortex here. Of course, there are even more sophisticated methods to visualize this vortex here, but for now this seems reasonable. Okay, so let's look here at the back, and again we see that here on the back we now have actually two vortices, right? The first slice that we did was here, where we saw this big recirculating vortex, and this is actually part of two vortices that recirculate here, right? So the flow separates here on this edge, and then it comes back to fill up the space on both sides, and this creates those two large vortices here on the back. So those are those two vortices here, and if you like, you can play around a little bit with it, of course. Maybe look at the other planes, whatever you like. We will continue with more post-processing next time. So I hope you understood how to generally visualize some simple things in Paraview. This is something that you want to do most of the time in order to assess if your simulation makes sense, generally speaking.